let's see. Okay, hopefully this style will work a little bit better. What I've tried to do is I've tried to take the time and work it out. Okay, now you don't want to look too far ahead, because what I'm going to do is I'm going to try to ask you questions. How would you approach this? How blah blah. But then the text is already there, and since we're recording, I'm just going to highlight things as we go through, and I'm going to say things to you, and I'm going to highlight them. Okay, so hopefully you don't have to sit there and stare at me while I write, wasting your time. Okay, and we can maybe have a little bit of a dialogue, okay? So that's kind of what I'm going to try and do, because, you know, recording and writing, that didn't seem to work too well, okay? So I'm going to try this technique. Okay, let's zoom in here. I think I can zoom it in. A little too much. Okay, so this is problem 1656. So if you have your book, you can look on that thing. At the instance shown, the disk is rotating with an angular velocity of omega. So that means they're going to tell me that. They're going to say it has this omega. And has an angular acceleration of alpha. So that's their way of saying, I'm going to tell you those. I'm not going to tell you the number now, but I'm going to tell you what they are, so you can pretend like you know them. Bless you. Determine the velocity and acceleration of cylinder B at this instant. Neglect the size of pulley C. Okay, so let's look at the picture. What is it that they want? What are they telling me? They're telling me the omega and the alpha. You see them there in the picture?
Yes.
Okay. What is omega, by the way? Give me a name for it. What is it? Angular velocity. And that would be the angular velocity of point A, correct?
No.
Why not? No, it's not. Why not? Yeah, right? But I'm making a point, right? It's a very subtle point, but you know, if you don't get this firm in your head, you will, I'll bet you, make mistakes. Okay? Omega is the angular, this is what I said, I think anyway. Omega is the angular velocity of point A. That's a lie. Why? Points have velocities, they do not have angular velocities. The easiest way to think about that, right? I mean, there's theory behind it. Okay, the easiest way to think about it is, how do you define angular velocity? How do you know that this object has or does not have angular velocity? You paint something on it. What do you paint on it? A line. Okay? So you paint a line on it. Use your imagination. That black guy's a line, right? What else do you paint? Paint a line where? On the ground, or whatever you want it relative to. Right? We talked about relative motion. So you could have the angular velocity relative to, and you would paint a line on that. When you say angular velocity, it's kind of assumed you mean relative to the ground. Okay? So what you would do is you paint a line here, and you paint a line on the ground. They can be anywhere, with one exception. I'll show you in just a second. The lines can be anywhere. And then you watch the motion. You watch the two lines, and if the two lines stay with the same angle between them, you say I have no angular velocity. Okay? So does this guy right here have angular velocity? No. Okay, you have to pardon my handshaking, right? No, why not? It's moving on a curve. But the angle doesn't change. So you can have different kinds of motion. This is, I don't know what your book calls it. I don't care what it's called, because most of the time engineers don't say, hey, what kind of motion you got? Right? Okay, so this has zero angular velocity, even though it's on a circle. Or an oval, or whatever that thing is. Get the idea? So moving on a circle has nothing to do, really, with the angular velocity. What about this one?
Yes.
Yeah, it does. Okay? That would be the angular velocity. How do you know? Well, because the lines are changing. Now I said you can paint the line anywhere you want. Okay, suppose I painted the line right here with my finger. Okay, and it's doing this. Well, it does have angular velocity, right? But it doesn't look like this line's doing anything. That's because you're rotating around the line. Okay, so you just have to be careful. And we're doing all 2D problems, right? So usually just any line in here would be good. The angle itself doesn't matter. What's important is, does the angle change? If so, it has an angular velocity. So you can choose a line like that, you can choose a line like that, you can choose a line this way, and what you'll see is that the angles are always changing the same. So for example, right here in the ground, parallel, correct? If you go like that, you move 90, right? You with me? Okay, what if it's like this? And I go like that. Still move 90. So it doesn't matter what the angle itself is, it's the fact that it's changing. Is that good with everybody? Why then, you know, just, I mean, there's theory, but why would you say you can't have an angular velocity of a point? Try to draw a line on it. You get a million of them, right? You see that? Now there's theory behind it, but I think that's the easiest thing. Oh, well, I can't get an angular velocity of a point because I can't draw a line on it. Make sense? Okay. So, all right, so in this particular case, omega is the angular velocity of the disk. Alpha would be the angular acceleration of the disk, and those things are told to me, so I know those things. And what is it that they want?
Velocity of B.
Yeah, they want the velocity of the cylinder B. So they want to know what's the velocity of this. Probably at some time, I think. Oh, okay, at this instant. Okay. At this instant, is it a time spanner?
No.
Okay, so what does that mean? It means that you're going to find the acceleration or velocity or whatever, and you're going to say, I'm done. If it was a time spanner, what you would expect is you would say, I'm going to have to find that acceleration or the velocity, one or the other, and I would have to solve the differential equation. I would have to integrate it. And the only way we do that is either by using the handy-dandy formulas that came out of chapter 12, or we actually we separate variables and integrate. Okay, so those are the only two ways that we know how to do that yet. Okay, so it's not a time spanner. Do I need a free body diagram to solve this problem? Do I need a free? How do you know? You're shaking your head no. How do you know?
You have one here before zero velocity.
We have one what?
Angular velocity.
Angular velocity. So what?
We can find all.
You can find them. How do you know you can find them all?
Rule of thumb.
Ah, degree of freedom. So what you know, if you say, well, I counted that in my head. Okay, good. That's where I want you to be, right? So what you'll do is, how many degree of freedom do you have? One. Okay, so you're telling me something can move in there. What can be moving? The disc? Okay, so the disc is moving. I count one. Hold the disc still. Okay, so pretend like you hold the disc still. Can anything move?
No.
I say the rope can break.
We're not.
Okay, good. No, all right, we're not, well, the guy can swing back and forth on the end of the rope.
Still.
Oh, you're not worried about that? Okay, then you got me. It's 1 degree of freedom. Yeah, of course.
If theta goes below zero,
That's a good one, right? And then it separates up and it'll be a totally different problem. Okay, so I'm going to assume that won't happen. How's that? But you hear what he's saying? If you rotated this clockwise, at some point, the rope would go straight from the center, straight over to C, and that'd be that. It'd be a different kind of problem. Well, not a different kind, but it would be different math that I would use. Come on. Okay, so it's 1 degree of freedom. What does that mean? It means if you give me one position, I can find all positions. Didn't say it was easy. If you give me one velocity, one dot term, a single dot term, I can find all other dot terms. If you give me one double dot term, I can find all double dot terms. That's what 1 degree of freedom means. What is it they want me to find? Tension in the rope. Uh-oh, I would need a free body diagram. You see how it's all kind of fits? It's the same thing I've been preaching to you before. It's just now we have things rotated and so on. No, that's not what they want. They just want a velocity or acceleration, whatever it is, for body B. I can do that with no free body diagram involved. Okay, so that's how I know not to go in there and do a free body diagram. Of course, what you want to do is do it kind of quickly. It's 1 degree of freedom, and he's giving me this, so you go with that, okay, boom, no free body, and just get on with it. You don't want to spend 30 minutes explaining it. Got it? Okay. So what I'm looking for is a way to relate one thing to another thing. And how many varieties of doing that do I have? I have one of these. I have loops. I've shown you at least one loop. And I think I showed you these guys right here. So any ideas of which one you want to try? See, I think before, if you had to relate something, you had rope and that was about it. Right? Now you gotta make a choice. Anybody got any ideas? Huh?
We could do the loop.
Do the loop, okay? Let's think about doing a loop. Where would you do a loop? I thought about doing a loop too. Okay, from where? From the center, okay, so it's gonna go like this. Come on. Okay, let me put a, I would start, say here, I think is what you mean. Can you see that? Okay. Start there, and what would you do? Right, he wants a loop, right? Go to where? Go to A, so you go up here. Okay, now what? Down to C. It's close enough, right? Don't you think? Because they're all the same. Okay. Now we're looks like a good loop, right? Okay. Let's take a look at what's going to happen to you if you did this. When you go from the center to A, you're going to get some good information. What's it going to do? It's going to bring in the angle theta. It'll bring in, when you differentiate it, it'll bring in a theta dot, and it'll bring in a theta double dot. That's good. That's why you want to, when you're doing loops, you want to walk down the bodies, because it'll bring in their angular stuff. Okay? So if you think about going from the center to A, you're going to write 3 cosine theta I plus, right? You with me? Right? Okay. What are you going to do when you go from A to C? Is it a constant? No, but you say, hey, I'm not going to worry about it. I'm going to call it a distance D or something. Not a problem. What directions are they going to go? Down and to the right. How much? Cosine of beta, you sine beta, right? You'll find it, you say, hey, no big deal. I got an R, I got a distance, and I got an angle. Okay, so far I got 2 unknowns in there. Then what are you going to do? You're going to go down how far? Y. Okay, you don't know it, there's the 3rd variable, right? Now what are you going to do? How far? Good, and there's nothing unknown. Man, I picked up something, right? Okay, and then what are you going to do? How far? Those 2 Y's are going to cancel out. One went down, one went up. See? So what are you going to be left with? A loop, right? A loop that's going to have 2 unknowns. Not a problem. I equal I, J equal J, right? You're going to end up with 2 equations. What are you going to be able to solve for? The distance between A and C, and the angle, whatever angle you happen to choose to write. You're going to be able to get those 2 guys. Did you get to where you want to be? Maybe a little closer, right? You agree? Maybe a little closer. You think you're going to be close enough? Let's think of something else. Maybe there's an easier way to do this problem. What formula? Yeah, you can use this formula. They work for everything. I'm thinking there's probably something even easier. I'm thinking ropes, right? And so now let's think about it. The length of the rope, is it constant? Okay, so then I can write the length of the rope and take a derivative of it. Okay, so let's think about what's going to happen. All right, do you know from the length of rope between the center and A, right? What is it? 3. Okay, that's easy, man. I can plug that straight in. What about from A to C? That's going to change, right? Do you think you can find a reasonable length or an equation for it? You're given theta. Yeah, so that one probably isn't going to be too hard. It'll look ugly. It'll be square root of something, but hey, I got Mathematica, right? So do you. And then what about from C to B? Piece of cake, right? I'm thinking rather than going and doing the loop, not that it won't work, But rather than doing the loop and all that, I think, bless you, I think it might be a little easier for me to write the length of the rope. So that's what I'm going to try and do. You with me? So what you want to do, now that you have a choice, you're going to have to sit there and go, degree of freedom, blah, blah, blah. Ah, it's not a free body diagram. Okay, good. Now I have a choice of what I need to do, and you're going to have to kind of choose wisely. Right? Okay, so let's take a look at what I did. So the first question I had was the loops. Do you want to use loops? We kind of talked about that. The other one was omega r. That's what I mean by these things. Not that you can't do it, but I don't know. But the length of rope seems pretty easy to me. Okay, so here's what I did. What does that guy say? This equation, right? What does this equation right here do? L equals, what's that 3? That's the radius of the guy. It's always 3 no matter where the guy is, it's 3. What's that big square root junk? Yeah, so right, here's the 3 sine theta. What is that? That's the vertical height of that guy, right? Between C and A. Isn't that the vertical distance between C and A? So it's a hypotenuse. Let's see if I can. Right. So this guy right here. Oops. Pick up the right pen. Right here. It won't pick up my pen. There we go. Right there. That's what this guy is. 3 sine theta. That's this guy, that height. You see that? Okay. And what's this? What's that term? Yeah, so it's 5, right? It's 5 minus 3 cosine, minus that piece right there.
You're supposed to have a square.
Oops, I left that off just to make sure y'all were paying attention. Right? So that's the Pythagorean theorem. Is that what that's called? Right? And then what's the plus y? Yeah, that's the distance that, hanging down from the beat. Okay, so now what are you going to do? What do you do when you have a loop equation? You take a derivative, correct. You take a derivative. Do you really want to do it by hand? You can. And when I looked at the solution manual, I cheat, right? I look at, just to make sure I'm not leading you astray, I looked at the solution. That's what they did too. They used a rope. They put in a hypotenuse like this with the square root. And then they just got a big stick and beat on it. Okay? Could you do that? Yeah. Do you want to do that? Maybe not. One derivative's not too bad. You want to see how it's done in Mathematica? Or can I just skip it and just post it? Skip it and post it? Okay. I will skip it and post it, but it's fairly easy to just punch that in. The thing that you have to watch out for is that you've got to tell Mathematica what's a variable. So you're going to tell it that theta is a variable. So when you type it in, whenever you get to the theta, and you don't have to make it a pretty little theta. For example, you can call it TH and say that's theta. You can write out theta if you want to. It's just more typing. And then how would you tell it that theta is a function of time? Yeah, you do a square bracket, not a parenthesis, and you go T. And that tells Mathematica, aha, when t changes, this thing will change too. It needs to know that, otherwise it'll think it's a constant and it'll take the wrong derivative. Okay? What else has to have a t behind it? The y. So here you would write this as a yt. And then to take a derivative, what you do is you say capital D, bracket, and then you put your equation. So you can actually type this equation, or you can name it something like L, 1 equal sign, blah, 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 blah. And then you can say take the derivative of L with respect to t. That gets you one derivative. Okay? Once you take the derivative, what do you really want to solve for? I think they ask you for the velocity of the beat. What's the velocity of B? Is it going to be theta, theta dot, something like that? Or is it y? Yeah, if you look at the equation, it's y, right? Because the position of B, we'll measure it from this point right here, that's fixed, right? The position of B is this right here. You take a derivative of that position, you get the velocity. Does that make sense? When you solve this, are you going to get a positive y or a negative y? Think about what's happening. Look at the picture and tell me, if I did it right, would I get a positive number for theta, or excuse me, for y, or would I get a negative y? Is y getting bigger or is it getting smaller? It's getting smaller, okay? So if it's getting smaller, I'm saying it's this way. It's negative. Oops, I'm wrong. It's the other way. Okay? So you should get a negative y dot. Y dot equals -3 or something. And you look at it and go, oh, y dot -3? I got it wrong. I said it's in the positive. I'm not. It's going up. Okay? So it's going to go up at a magnitude of 3. I think that's all it asked for. It didn't ask for the acceleration. Right? But you could find the acceleration, couldn't you? Oh, does it? Okay, then how would you find acceleration? Second derivative. Do you want to do that by hand? First derivatives aren't that bad, even when they're ugly. Second derivatives, man, it gets crazy. Okay, so I'll post that. I'm going to forget, so just email and say, hey, you remember? Hey, you promised to post it. I'll post it because I've already done it out. So far, so good? You tell me what was hard about this problem. What's hard about that problem? Was it hard to find the degree of freedom? No. Was it hard to know whether or not you needed a free body? Was it hard to decide which technique you wanted to use? Maybe. So that's what you need to practice on. Okay? Maybe. But was it hard once you determined the length of the rope, or that's what you were going to use? Was that hard? It's tedious, isn't it? Kind of tedious. And then taking the derivative. If you don't have Mathematica, that's where you're going to spend 20 minutes. Okay? But that's what the solution manual did as well, and it's this long. One derivative. Man, because it's got a lot of terms. Okay? Any questions? You want to do another one? All right, let me pause. Any questions? People say I don't wait long enough. I'll be back after I get some coffee. Is that waiting long enough? Okay. Your exams are graded. I gave them to the TA to put into the spreadsheet and upload onto Blackboard. She said she would. She's getting on that. And so your grades should suddenly appear on Blackboard. And then I told her that she has to figure out how to get them back to you in a timely way. Okay? All right. I think we did this one. I'm not sure. 41? Okay, so we don't need to do that one? Okay, how about this one? All right, let's zoom in. And again, don't cheat by looking at what I did and then say, oh, yeah, I'm really brilliant. Okay. Here we go. Crankshaft AB is rotating at a constant angular velocity of omega. Determine the velocity of the piston P at the instant theta equals 30 degrees. Okay. Do I need a free body diagram? Why not? Nope. Started out wrong. Why not? I mean, you may have already done this, right? You say, well, I already did that. Okay. What do you do first when you're faced with that question? Do you need a free body diagram? You count something. What are you going to count? Degree of freedom. Okay, so let's count the degree of freedom. Can anything move?
Yes.
What?
Crank.
The crank. Okay, so AB can move, right? Can you visualize what it's doing? It's I'm not sure if I can do it. Here's AB and here's the other guy. And what's happening is this guy's coming down like that, right, and then turning around. And, okay, get the idea of what it's doing. Okay, so yeah, one thing can move. Okay, boom. Stop the crank. Can anything move? Not unless it breaks, not unless it comes apart, right? So how many degree of freedom is it? Okay, what does 1 degree of freedom mean?
You only need one motion.
Exactly. If you give me one position, I can find all positions. If you give me one dot, I can find all dots. If you give me one double dot, I can find all double dots. What I can't do is if you give me a double dot, I can't go find anything else unless you give me the history of the double dot, because then I can integrate it, right? So let me give you an example. I'm in my car. I'm doing 100 miles an hour, and I'm headed for Las Cruces. That's all you know. Right now I'm doing 100 miles an hour. Where am I? In my car. Very good. In my car. That's a good answer. I would have said I don't know. But you get the point. Just because you have a double dot, just because you have a single dot velocity, right, 100 miles an hour, you have no clue where I'm at. But if I were to tell you I've been doing 100 miles an hour constantly since I left El Paso, it's now 5 minutes later. Now I'm giving you a history, right? And with a history, you can integrate it and find out where I am. You see the difference? So what's happening with degree of freedom is right now, if you give me one double dot right now, I can find all double dots right now. See how that works? Okay. What is it that they want me to find?
The velocity of piston P.
Yeah, I think it's the velocity, right? We have to change that. Okay. The crankshaft has blah, determine the velocity. So they want a dot term of the piston at the instant theta equals 30 degrees. So do I need a free body diagram? No. If they were to say, you know what, I'm worried about this 1 kilogram piston, they're not that heavy, 1 kilogram piston flying off of this, I need to know the forces right there at that pin. Now you're going to need a free body diagram. You see the difference? Okay. No free body diagram. Okay. What is it that they want? They do not want, they want the velocity of a piston. Okay? So how am I going to find the velocity of that piston? I've got several things I can do. How are you going to find that? What's the easiest way you think to find that acceleration or velocity of the piston? Okay, we're going to use loops. What do loops do for you? They relate one to another. That's what they do. Okay? Do you really want to relate something? You will, right? But what I'm thinking right now is, well, I need to find out what I need to relate. What do I need to find? So what I want is, give me the velocity of the piston. And I look at my options and I say, you know what? Looks like if I take a position and differentiate it, that might be the easy thing. What would be the position? You can measure your positions from any fixed point, okay? Measure your position of the piston from any fixed point and then differentiate it.
Well, we did dx.
Very good. So you're ahead of me. So right, what you're thinking is, hey, I tell you what, I can write the position of x, or the position of p. The position of p is, how about we measure it from point A? Is that good? A is fixed. Okay, where is p if you start at A? X in what direction? To the right. Okay, so it's x to the right. See how easy that is to find the position? Piece of cake, right? I'm not relating now. I'm just finding position. And what do I want to do with that position? Take a derivative, right? So that I get the velocity. The derivative of position is velocity. So the velocity of P is equal to, can you give me the derivative of that real quick, like? X dot? Now I know what I need to relate. What I want to do is I want to relate the thing I know. What do I know? I know the angle dot, right? I know the angle dot. What I want to do is relate that to X dot. That's my relationship. You see it? Now, how do I relate them? Do I have a rope? Nah, that's kind of dumb. What other things have I got? Oh, I've got this new stuff. Ooh, cool. You want to do that? You do? Another problem. I don't want to do it here. How about loops? Well, you can do it, okay? I don't mean you can't do it. I just don't want to show that right now. I want to beat you over the head with a loop, 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 so that you're good at loops then we'll move on to using the others, okay? So it's not like it's wrong, I just don't want to do that right now. Because I'm trying to take you somewhere. Somewhere good. So I'm gonna use loops. Why did I choose that? Because I want to teach you a loop. I want you to get some practice at loops, and it relates things. That's what it's for, to relate things. All right, so let's use the loop. All right, now when you're using a loop, how do I get started? And don't look down here. Right? How are you going to get started? Yeah, you're going to walk along the path. And what you mean by path is you walk along all of the members. Why? You don't have to, but usually it brings in fewer unknowns, and it brings in the things that you want anyway. So walk along the path, right? Along the members. Where do you start? Do you always start in the middle? Do you always have to start at a fixed point? You can start anywhere you want. Just start there and come back to there. That's the only thing that's important, okay? To me, it looks easy to go from A around the loop. How about we do that? Okay, you do it. You see the answer, but I don't want to show it to you. You do it. Write me a loop equation. If you don't know what I'm talking about, raise your hand. I'll come and help you. And if you want to earn a poker chip, oh, you do? Okay. You have a question or you want me to come back? You have one? No. Okay, anybody else need help? You got it? What do you need? Let me give you just a hint to get you all started, and then you'll see if this helps you. Okay, I'm going to go from A to B. You start anywhere, but A to B looks like a nice place to start. If you're going to walk from A to B, I'm going to walk this far. How far is that? 0.2 cosine theta. So I'm going to walk 0.2 cosine theta. Which direction? Up, down, right, left? Okay, to the right. And I always take right positive. I don't know what you guys want to do, but that's what I do. So that'll be an I. And then what? That walks you over to here. And then what are you going to do? You're going to go up. How far? 0.2 sine. 0.2 sine theta. J. So what do I mean you walk along it? Well, you're using these variables that belong to it to get over there. So you say, I'm going to go this way and then up. So basically, I've gone along that. Does that help?
You couldn't just say 0.2.
You could say 0.2, but in what direction? Nothing wrong with it, but you'd have to say 0.2 in this direction. It's not I, it's not J, it's a combination of them. If you can figure out how to get a vector in that direction, yeah, sure. And in statics, they taught you how to do it. So I'm not saying it can't be done. I'm just not going to beat you with it, right? But yeah, in statics, they taught you how to find a vector, and given a point, you find the vector. It can be done. I just don't want to hassle it. I think this is easy too. Now what are you going to add on? That's just one piece. Yeah, exactly. 0.75 cosine of beta. And that'll get you over to here. You're too high. Now what? Minus 0.75 sine beta. Boom, you're down, you're right there. Now what are you going to do?
Wait, can you repeat that last thing you said?
Tell you what, I will show it to you. Bless you. See it right here? Right? Well, where did it go? This piece right here. Whoa, man. Yeah, I agree. Right there. What is that? What are you doing? What's this piece? You're going to the right, 0.75 cosine beta. Right? That gets you up over the piston, right? What does this piece do? It brings you down, right? So basically, I've walked along this rod because I'm using its variables. Yeah.
I have a question. Instead of negative sine of beta in the J, that I had said negative 0.2 sine of J of theta J. Like in,
So you made this one negative. Is that what you're saying?
no, you already have that one, but just put a negative next to it because they cancel at the end, right?
I don't know what you're talking. You're confusing me. Hold on to that. I'll look at it. What you have to do is go right, up, right, and down. So there's different ways to do it, and you may have some right. I just don't understand it. And rather than say no, you're wrong, and confuse you, let me look at it.
I think he's saying the vertical distance in the middle is the same.
You can do that, all right? What he's saying, and this is in the old way, before we had Mathematica, what they would teach you is they'd say, look at that. You see that? Use the law of sines. Use hypothesis, whatever. I mean, there were all these wild, crazy tricks. They would say, use the law of cosines, blah, 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 boom. And they were looking for easy, quick answers. You can do that. I'm not going to count it off. But in order to use a lot of shortcuts, you got to remember a lot of shortcuts. And what's going to happen is you may remember them for the exam. That's fine. You'll pass. I won't count it off. You'll get out of here in a year, and you won't remember any of that stuff. And so when you're out in industry and somebody says, or they won't say do this problem, but if you're faced with something, you'll go, man, I don't remember any of that crap. So that's why I try to teach one thing or a minimum number of things, okay? But you're not wrong. What he was saying is, why can't we use this height over here to match up with this guy over here? Yeah, no problem. You're finding your own equations. That's fine. The loop is a standard way to do it that always works every single time. But you take your pick. And then what's this term right here? Yeah, so what you're doing is you're coming back from there straight across over to there. How many unknowns are in that equation? Theta's known, right? X and beta, two unknowns. How many equations, bless you, how many equations are you going to get from that guy? You're going to get the I equal to the I. You're going to get the J equal to the J. You're going to get two equations. Can you solve them? When you do loops in the real world, the hardest part is getting the angles. That's the hardest part because it's nonlinear and it's not easy to solve nonlinear, right? It's got sines and cosines. It's not easy to solve those equations. It can be done, but that's the hard part. Okay? So, what I do is, I cheat a little bit sometimes. So, I know that finding the angles is hard, so I came up with this formula. What is that formula?
The relation between the angle and the...
Yeah, and it's a law of something. What is it? Law of sines. I don't care. Use the law of sines. I can remember the law of sines. I use it a lot, okay? And I remember loops. If you remember the law of cosines, half-angle formulas, man, there's a bunch of them. If you remember them or you have them on your cheat sheet, use them, right? The hard part is getting the angle. This equation is not so bad. If you give me the theta, I think I can get the beta. You with me? Okay. Mathematica, what I do with Mathematica is I give it this one and say, you find all of them for me. Thank you very much. And it does a pretty good job. Okay? But in the old days, I would have done this. Because I had to do it by hand. And, man, solving transcendental equations with signs of, oh man, that wasn't easy. And so we would forget the loops and just try to do by hook or crook, find out the angle. Okay, now let's say you have the angle. What are you going to do? Where did this come from, by the way? Where did this guy right here come from? Exactly, it's the I equation. Look back here at your loop. You have 0.2 cosine theta. You have plus 0.75 cosine beta equals, or minus x equals 0. So you just take the x to the other side, bang, there's your x. Okay, so what you do is they give you the theta, you take the theta, put it into this equation, get your beta, take your theta and your beta, put it in here, now you have the x. Nobody cared, but you do have it. You want x dot, right? If this is x, can you take an x dot? Okay, so you can do that by hand right there. Do you know everything you need to know? Do you know theta? It's 30 degrees, right? Do you know theta dot? Theta dot's right here. You know theta. Theta dot. Right? So you know this thing. You know the theta. You know the theta dot. Do you know the beta? You solve for it. Do you know beta dot? How are you going to get it?
You know the theta dot, so you can find it.
Yeah, so what you're going to do is you're going to come up here. You're going to come up here and you're going to take that equation right there, take a derivative of it. Now you got a beta dot. You solve for beta dot, put it in. Or you look at the Mathematica file that I'll upload and you'll see that it goes boom, like that. Okay, it's your choice. So it can be done by hand or it can be done with Mathematica, your choice. How about taking the second derivative of x? It's not written down. Do you think you could if you had to do it by hand? Right? So what you're going to do is you're going to take the derivative of this one times theta dot, so you'll end up with a theta dot squared, right? Chain rule. Or you're going to open up Mathematica and have it do it. It's your call. Everybody okay with that? Problem solved, correct? You want to do another one? All right. Y'all do this one. Get together in groups if you want to. And I'm going to try and make rounds and make sure that you're doing it okay. Does anybody have a question about the previous one while the others start this one? Okay. Yeah, his question was they only asked for the velocity, so we only took one derivative. Yes. But if they ask for acceleration, you do two derivatives. It just gets, the algebra just gets wild. I think that's why they didn't ask you for it. Incidentally, you get these huge, huge numbers for acceleration on that piston. It's not rotating very fast, but you get huge accelerations. And that happens a lot inside machinery. You had a question?
No, I was asking, you were talking about this problem with
Yeah, the other one, you know, that slider crank, huge accelerations, and so you get large forces inside your engine. That's why you throw rods and stuff like that. Okay, who's got started on it? Who's got started? Yeah, man, I better be careful when I record myself. I say, man, that guy's an idiot. How did you start? You started writing stuff down, turn off your brain, right? Better be careful. because on the exam, it's gonna cover chapter 16 and 17, there will be free body diagrams. So you better know which way to go. How do you know? What'd you count? Degree of freedom, okay. Can anybody tell me what the degree of freedom is? 1 degree of freedom? Are you sure?
Yes.
Okay, what's moving?
Hydraulic.
Yeah, the hydraulic cylinder. All right, stop the hydraulic cylinder. Can anything move? Okay, 1 degree of freedom. That means if I give you one motion, oh, I did, a single dot term, right? And a constant. So the double dot is 0. So you've got a dot and a double dot. And what do you want? Angular velocity, that's a dot term. Angular acceleration, that's a double dot. So I'm giving you 1 dot, and you need a 1 degree of freedom. So this is no free body diagram. So what do you want to relate? The 0.5 to what? Angular velocity. Can you see a variable up there that gives you the angular velocity? Or at least, right, that you could differentiate?
Yeah.
What is it? Theta, right? So if you take the derivative of theta, that's the angular. How in the world did you know that? Well, here's a line. Here's a line. I guess I better write it on here. There's a, to find angular velocity, you have to draw lines. Okay, here's a line. Right there, right straight down that slot. Draw a line on the ground. Okay, there you go. The change in the angle between those lines, theta dot, is the angular velocity of that rod, by definition, right? So, yeah, you knew that. Okay, what are you going to do? You need to find a relationship, right? Here are your choices. You want to use a rope? That's a dumb question, right? You want to use these? They're okay. They work for everything. So when in doubt, use this, right? But I really don't want to cover that. Loops, okay? How about a loop? Can you write a loop? Write a loop. Yeah, you just need to say what direction it is. Oh, yeah.
Because they tried to make it confusing for them.
Right, go the direction that makes sense.
Okay.
Question down here was when he does a loop, he chose to go counterclockwise. And he said, do I have to do it that way? No, you can go clockwise, counterclockwise, you can go any way you want. Where do you have to start? Anywhere you want. So you can start at D, like dog, you can start at A, you can start up there at B, whatever floats your boat, whatever you see easiest, use it. What he was doing over here, what he was doing in his loop, he had a good loop, but what he did was he used the angle theta 45, right? He said, oh, this is 45, and he put in a radius times the cosine of 45, right? What's wrong with that?
And it isn't in the higher J direction, it's a combination.
Well, okay, yeah, but okay, he did put in an R cosine 45I, and he put in an R sine 45J, so it's not the I and J, he did that, okay? What's wrong with calling it 45?
It's
Theta's
changing.
gonna be changing.
Theta is changing, right? So what'll happen is if he isn't careful, see, he'll have, this is a piece of his loop. He'll have, I forget what he had here, but R, that'd be the length along here. R cosine 45 I plus R sine 45 J, right? Nothing wrong with that. That's what it is right now. Then when he takes a derivative, what's he going to do? He's going to have an R dot times a constant. Is that the right derivative? No. He should have an R dot, and he should also pick up a theta dot, right? So what you want to be careful of is only put in constants if they're really constants. If they're not, call them a variable, because otherwise you're going to get fooled and forget to take the derivative of it. Totally different, right? And the same thing they teach you in calculus, right? If you have to take a derivative and find the value when time equals 0, don't put a 0 in and then take a derivative. Don't do that. You take the derivative, then you put in the number. Got it? That's what it's always been. So what you've got to do when you write your loops is say, I know that's 45 now, but I need to call it a variable, so when I take a derivative, I will get the correct derivative. After I finish my derivatives, then you shove numbers in. Got it? Okay, keep going. Oh, I see what you're doing. This is the I component. But you know that they. So you got to. how often L equals? Inverse cosine or cosine? R cosine. Okay, here's his question. I'm not sure where he came from, right? Y'all are being very creative with your loops. Nothing wrong with being creative, but make sure that whatever you're creating, it's right. Okay, make sure that it's right. Okay, so where did you get this equation? What is L? What's L? Length of what? Of what loop? All the way around? I mean, there are other ways to solve it. I'm not saying this is the only way. I'm going to try and teach you a way, right? L is what? From here to here or what?
Yes.
That's L. Okay. The hypotenuse, maybe? Is this correct, class? What's the R? What's the R? This is R? I thought you said this was L.
No, you said the L was the length of this loop.
Yeah, see, I don't understand length of the loop. I don't get it. Okay. Let's write down some loops, okay? I'm going to show you my loop, and then if you have a loop that's different, you let me know, and then we'll discuss it. Make sure that everybody, because there can be more than one. Okay, I didn't do it yet. So here's what I'm going to do. I'm going to call this distance right here, I'm going to call this L, because I don't know it, okay? I'm going to start over here at point A, and I'm going to walk along that slot. So I'm going to go to the left. How far left am I going to go from A over to B? L cosine theta. And I'm going to go left. That's a negative I. I'm going to go up. How far am I going to go up? Up. Now I'm standing on point B, correct? Okay. What do you think I'm going to do now? I'm going to go down. Okay, so I'm going to call that distance right there Y. I don't know why. Now what? Now I'm standing on D as in dog. What? To the right. How far? Is it always 0.6? Okay, good. Plus 0.6 I. What's this equal to? Why? Because you're back where you started from. You went nowhere, right? Equals 0. That is a valid loop. Is it the only loop? No, because somebody over here, instead of using L sine theta, he had something like y over cosecant or something, right? And I think that's right, but man, I can't think about cosecants, right? Right? So, hey, he's on his own. I think it's right, but you got to make sure you go around the loop. Now, see, here's the thing about yours. I don't know where your equation came from. This L. Is my L your L, or you have some other L?
I just changed your L by my R.
Okay, so if I call it, okay, so your R is what you're calling L. Okay, so in other words, what you're saying is this guy is R, correct? Is that okay? So what you're writing, now what are you calling L?
L is the length of the hypotenuse.
Okay, isn't that R? Okay, so then what you're saying is this, right? This is what you're saying. You're saying L equals minus L cosine 45 plus L cosine 45, sine 45. Isn't that what you're saying then? Right? Divide through by the L. Boom. Boom. 1. Is that true? It is? Sine of 45 minus cosine 45 equals 1. Is that true? I don't know where you got it, but it is not true. I don't know where you got it. But do you see what I did? Does it make sense? Whoa, man. Let me highlight this guy right here. I think you're trying to do something like that, right? But I don't know what you were thinking when you came up with your formula. It's not right. Okay? Okay, who else got something that's different? Okay.
Well, no, I was gonna ask you, because I thought about canceling or just taking out the L sine theta and Y, but I don't know if that's, because I would think that they would be the same but opposite in any case.
Yeah, and that's what they are, right? Because how many J's you got over here? None. So that says that L sine theta equals Y. Now, you know, I didn't say loops are the only way, right? So you could sit back like that and say, you know what, this is a real simple triangle. That vertical height over there, Y, that's equal to L sine theta. Boom, write it down. Write it down, it's good. If it's true, it's good. This isn't true, I don't know where it came from, it's no good, right? I won't stop you. You look at that triangle and you say, got it. Y equals L sine theta. How many unknowns you got in that equation? Two. Y and L. Right? So you need another equation. Where are you going to get your other equation? Okay, where? What are you going to say? I mean, I assume you're looking at the triangle, correct?
Yeah.
So where are you going to get your other equation?
Y squared plus B squared.
That will work. You could also say L cosine theta equals what? 0.6. Two equations, two unknowns, you got it. I'm not saying that stuff doesn't work, but what if it wasn't a triangle? What if it was a parallelogram or something? You know, I mean, if you're good in this is just geometry. If you're really good in geometry, you say, forget those loops, man. I can write down the answers because I'm good. I won't stop you. All I know is I ain't that good. And I want a method that works, period, boom, bang, not just for the simple things, but works, period. Loops work, period. Okay?
Then you're counting the L from the point on the bottom to where it's touching.
It's the hypotenuse.
Where it's touching the piston and the pin, or the A to C or A to B?
In my equation, L goes from A all the way up to B. It's the hypotenuse of that guy.
So you really don't need C then?
Huh?
How's it going?
Okay.
So what's C for? You don't need C, right?
Nope, not at all. Okay, here, since you brought it up, you can blame him. Here's the theory. When we begin to use the omega R business, here's what's going to happen. You only need to use that equation on special points. Write this down. This is a note. This is coming up. When you use the omega cross equations, okay, when you use the omega cross equations, you're using points. You got a billion points. You do not use it on a billion points. You use it on special points. They've got to be special, right? What makes a point special? Number one, you want to know something about what it's doing. Because the problem says find the velocity of C. Okay, it's special. You want to know something about it. Number two, it's a point that you know something about. I know something about it. Like, for example, is A special? Don't you know it's in permanent contact with the ground? Doesn't that mean it has the same velocity as the ground? Doesn't that mean you know something about it? Is it special? Yes, it is. You know something about it. Is point D as in dog special? Yes, absolutely. It's special. The third reason that makes them special is they touch more than one body. Not necessarily permanently, but they're touching more than one body. Okay. Is B as in boy special? You don't know anything about it. Do you want to know something about it? Is that what the question asked? What's the velocity of B? you know something about B? Not really. Do you want to know something about B? No, not really. But why is it special? Touches more than one body. That makes him special. You only write the omega R equations on special points. Okay, so his question was, does C matter? Well, is C special? Do you know something about C? No? It's motion? No. Do you want to know something about C? No? Does it touch more than one body? Then they're throwing it in there to confuse you. Has nothing to do with the problem. Okay? All right. What other questions we have on this? Okay, so you see my loop. How many unknowns are in my loop? What are they? L, Y. Is theta unknown? No. Theta was given as 45. 2 unknowns. How many equations are in my loop? 2. I equal I, J equal J. They're going to balance, and then I can pull them off and solve. This is just a triangle. It's probably just as easy. Just say, look, I remember L cosine equals this and L sine equals that. That's fine. I won't count it off. But if you can't do that, then you need the loop. Yeah.
Yeah, I think you can get rid of the L, or at least that's what I tried to do, by writing the distance of the.
Sure, sure. What he's saying is I don't need the loop. I can do it by looking at the geometry. Yeah, that's what I just told you. If you look at the geometry and say, look, I know that y over 0.6 is the tangent of 45 degrees. Yeah, do it. Go for it. But if you see a problem where you don't have a triangle, and they will occur a lot, then you're on your own. Okay? So I would suggest, even though you don't need it, practice the loops on these simple problems so that when you have to have it, you know how to use it. Oh, come on. Right? So I'm not telling you have to use a loop. I'm just telling you loops will work for everything. Do what you know is right. And don't make mistakes like he did, where he wrote something that looked right and is not. Okay, so be careful. Can we go on to the next one?
Yes.
Okay. What you would do here is the same boring thing. You would take off the I equal I, J equal J, and you solve for your angles, or you use your law of sine, whatever. Then you would take what? The derivative, and then you would solve for the dot terms. Then you would take a double derivative, and you solve for the double dot terms.
Will L be constant or?
Is L constant? No, L is not constant. Yeah, so when you put it into Mathematica, you're going to have to say L bracket T, is cosine, is the angle theta constant? Nope, so theta T is Y constant? Nope, YT is 0.6 constant? Thank goodness, right? Okay, so you could punch it in. If you remind me, I will post the Mathematica. Ready to do another one? I'm not sure no, I don't think we did this one. The angular velocity of the disk is defined as blah, 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 where t is in seconds. Determine the magnitude of velocity and acceleration at point A on the disk when t equals 0.5 seconds. Okay. Is this a time spanner? Okay. So it looks to me like what I'm going to do is I am going to probably integrate something. That's what I'm thinking. Okay, so what I'm going to do is I'm going to try and find the velocity and acceleration of a point. Okay, so here we go. I want to know if I need a free body diagram. Obviously I don't. It's chapter 16. But how would I know? What do? Don't read it, but what would you? You're going to count the degree of freedom. How many degree of freedom is it? 1, yeah, because you can read the chart, right? 1 degree of freedom. Everybody okay with that? Okay. So what does that mean? It means you can find, if you tell me 1 position, 1 dot, and 1 double dot, I can find all the other positions, dots, and double dots. Right? So What do you want? Oh, you want velocity and acceleration. Oh, you want a dot, and you want double dots. Hey, piece of cake. This is not a it's not a three-line diagram. Everybody okay? All right. I would like to find the velocity of a point. Okay, is that what we use loops for? No. What do loops do for you? Relate. They are your relationships, right? So loops are your relationships. So you're going to try and use a loop on this guy?
No.
No. So let's cross that guy off. Okay. You got any ropes in there? Besides, what do ropes do for you? Relationships. That's not what I'm talking about, right? Okay, how about taking a position, differentiating it? Yeah, but, you know, that was chapter 13, 12. I want to do something different, so I'm not going to do that. I'm going to use this one now. Okay, the omega r. Okay, when you're using omega r, you have to identify the special points. Where are the special points here? They're marked. C. Why is C special? You know something about it. It's permanent contact with the ground. It's got to have the ground speed. Okay, then I know the velocity of the center is 0. Acceleration is 0. So I know something about it. That's what makes it special. Why is A special? I don't know anything about it. About its speed. I know it's on the rim, but I don't know its speed. Why is A special? It's not touching anything. Because I want to know something about it. So A is special, right? Any other special points? Okay, I'm only going to write equations between the special points. Now, here's a note for you. You ready? If you have 2 special points, you're going to write 1 omega r equation. If you have 3 special points, how many omega r equations do you think you're going to write? 2. It's always 1 less than the number. Why? Because if you have 3 special points and write 3 equations, the third one will be dependent. You'll be able to take this guy plus this guy and get the third one. Okay? You can do it, right? But I've done it, and every time they are independent. They are dependent. So 3 special points, 2 equations. What if you have 5 special points? 4 equations. I think you got it now, right? Okay. So I'm going to use that guy. Okay. I now know I've got A and I've got C. What's this equation right here do for you? What is that? Where does it come from? Right here. Velocity of a point, A, equals C plus omega. What omega? The body they're on, the disk, cross R. From where to where, okay? It goes from where to where if you're looking at this guy. Starts at the C, the point on the right-hand side, goes out to the other guy. So it starts with the point that's on your right-hand side and goes to the left-hand side point. So it's going to go that direction. Got it? How about the acceleration? They asked for the acceleration, so I'm going to write it down. There's the acceleration equation. Right? I'm not sure if your book writes it like this. Does your book write that? Who knows? I'm asking you whether you read it, right? You're not going to do it. This right here, omega squared r, that only works for 2 dimensions. We do so many 2 dimensions, I'm going to let you memorize that. But if you ever do a 3D problem, you go back to the book and you pull out the real equation. It goes omega cross r, and you'll have to do 2 cross products. Pain in the neck. It's not hard, it's just a pain in the neck. I'm going to let you get by with omega squared r. Yeah, you have a question?
Shouldn't it be CA, not AC?
It goes, you can use whatever notation you want. This is the notation I use. I know I have it correct because I do like a ratio fraction game. I take a C on the top and I multiply by an A over C. The C's cancel out and give me a 1. Leaves me with an A on the top, and that's what I have here. That's the way I memorize it. You say, that is ugly? Okay, fine. You call this guy George, you call that guy Harry, and it always goes from Harry to George. Whatever. But make sure that you know which way it goes, because it matters. Got it? You come up with your own way of memorizing it. Write it down, block it. I don't care. Do something. this guy goes from this point to this point. It always does. It always goes from this point to this point. So in this case, where does it go? Let me draw a picture of it. Which way does it go? It goes from here to there. Has to, cannot do anything else, or else you're using the wrong formula. Got it? Okay. All right, so what are you going to do about this? What are you going to do about this guy that's in the yellow? What do you know? Omega? Right? Yeah, omega's given. What about the R? Do you know the angle so that you get the I's and the J's? No. Okay, remember there are two kinds of problems that I'm going to introduce you to. One type of problem is where you're going to actually have to grind it out, do a cross product, beat it over the head with a big stick, and beat it into submission. Those are the kinds of things that will happen to you in the real world because you're doing very complicated problems. In order to pass system dynamics, and in order to get licensed to be an engineer, they are going to ask you questions, and those questions are going to be a lot easier. And they will be a lot easier because one of the points, for example, will be fixed. If point C is fixed, what do you know about VC? 0, and that's why I crossed it off. That guy is 0. So the velocity of A is omega cross R, right? It's perpendicular to omega. It's perpendicular to R. Can you visualize which way it's going? Where's the R? Right there. It's got to be perpendicular to my arm. It's going that way. Why that way?
That's the way of the rotation.
Got it. Yeah, here it is. See the arrow? Here's the rotation. So it's going like this. You see that? So you're looking at the arrow, the way it's rotating, it's going like that. So this is the speed of point A. Got it? I do not then need the cross product. What I need is I need the magnitude because I know which way it's going. What's the magnitude? It's omega times distance. What's this distance here? 0.8. So what will happen is when you come down here, what is this thing right there? Whoops. Darn it. What is that? What's this? 5t squared plus 2. What is that? That's the omega. What's this?
That's the distance.
That's the distance. So you can do the cross product if you want, but what they're expecting you to do is to say, oh, I know this is real simple. This guy's tied down. That omega cross R has got to be perpendicular. It will be. And its magnitude will be the size of omega times the distance. You get that? So you can do the cross products, but what I'm trying to show here is you don't need to on simple problems. They don't want you to on simple problems. They want you to be able to get it quick without having to do a cross product. You with me? What am I going to do about this? They want the velocity, right? Plug and charge, baby. You know the time is half a second. Can you go in there and get the speed? Okay. You know how big it is. Can you, on an exam, show me which way it goes? Yeah, so on an exam, I'd expect you to give me this number, and you'd show me this arrow. And that tells me you know what you're doing. Okay? How are you going to find acceleration?
Right.
Yeah, what you're going to do is you need the alpha, because you're going to plug into the formula right here. Alpha. Right? So you need to find alpha. That's d omega dt. Can you take a derivative of that? Piece of cake, right? So you get the alpha. This piece right here, which way does he go? Right, it's going to go, he's just like this guy, he's pointing down that way. That's the alpha R. Right, so it'll be alpha times distance. Right? What about this term? Which way does he go? No, he's not going in a circle. This is a number, this is your direction. Where is this? It's this way. Is he going that way?
It should be inside, right?
Huh?
It should be inside.
Yeah, he's not going in the plus R. Which way is he going? Minus R. He's going this way. Right? You know that. It's the normal component of acceleration. It's always inward. Right? It's always inward. Okay, if you want the magnitude of it, there's the acceleration. You see it right there? There's that piece that's along the tangent. There's your normal piece. How are you going to find the magnitude of that? Square root of the sum of the squares, right? Piece of cake. Boom, 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 boom. No cross products. Everybody good? Okay. I have to leave town today. I won't be at office hours in the afternoon. Sorry. You should have everything else. I will post more recordings, etc. When I can when my work schedule lightens up. I'll see you on Monday. And we didn't get a quiz, so the quiz is going to happen on Monday. It'll be over the stuff that we've done now.
That same relationship you used right there is the one you use for like gears of different sizes, right? Like omega R, omega R.
That's exactly right. So, for example,
But is it omega R or omega R? That's what I
here, I'll show you.
I know they have the same velocity. That point.
Right, and how do you know that? Okay, temporary contact, no slip. Temporary contact, no slip. It says velocity of E equals velocity. Or you say, this is officially what happens. If they're slipping, this could be a rubber here, so the reason they use those kinds of things, they want them to slip if something happens. Like somebody breaks this one suddenly, you don't want to break the gear, so it'll slip. And if it slips, then they're not the same. Right? But anyway, you're right. These two velocities must have the same speed because they happen to be in temporary contact without slip. That's why they have to be the same. Okay. So what you'll do is you'll say, oh, easy peasy. This guy's fixed. This guy's fixed. So this speed is omega. We'll call this A and this is B. It's omega A times the distance between here and here. This speed is equal to omega B times the distance there. That's omega cross R, omega cross R. Okay, now, if this guy is this way, which way is Q?
I don't think he wants to be pretended to be separate.
Yeah, point.
Oh yeah.
Like if you were testing you guys
Down. So this guy's got to go down this way. So which way is the omega? The arrow here or arrow there?
I think they want to be a little bit more.
So there's my positive omega A, there's my positive omega B. Then this is how they're related. Omega B equal to EA over EB. And this is what you ask me to true that. Because the velocity is but what happens if these were rubber gears that slip? Okay, they won't be this.
Really.
This thing is on a car and moving this way. Then it won't be this.
Thank you.
Yep. Sorry. Time got away. No problem. Yeah, let's go in the hall. Sorry.